Section 8.7, sizing the cam. Sizing the cam means that we're going to define the shape of the cam given the motion profile that we have defined. The motion profile that we have defined are the S, V, A, and J curves of the previous sections. And now we're going to determine what the shape of this cam is. Well, let me say it like this. The S, V, A, and J curves determine the shape of this cam. What we're going to now determine are the X and Y coordinates. If this is the origin of the cam here at the center, we're going to determine the coordinates that a machine tool would need to follow to cut out the surface of that cam. Before we get into those equations, it's important that we go over a few definitions for this cam geometry. And these are things like the prime circle, the base circle, the pitch curve, and the eccentricity that we have. The eccentricity, and this is relevant to this particular roller follower radial cam that we're dealing with here. And this is a translating roller follower in this case. And the motion of that roller follower is back and forth along this line. And that line is, you can set up another line parallel to it that goes through the center of the cam. And the fact that there's an offset there, that is called the eccentricity. So that's a value that we're going to need to deal with. There's also a pitch curve. The pitch curve is the radius that goes about the cam. If you were to take the follower and move that follower around the cam, you can see kind of a dotted line of that follower here, impression of it. And so as it goes around the cam surface, everywhere that center point goes is called the pitch curve. There's also a base circle. The base circle is the circle centered at the cam center, at the center of the cam, and it's the smallest circle that we can get that is still tangent to the cam surface. And you see here it's tangent. Can't get any smaller. If it got any smaller, then it wouldn't be tangent to the cam at any point. The prime circle is similar to the base circle, except that it is extended by an additional radius, and that radius is the radius of the follower that you see here. So here's the prime circle. So these are the various items I just went over. So our base circle is the smallest circle which can be drawn tangent to the physical cam surface. We have the prime circle, the smallest circle which can be drawn tangent to the locus of the center line of the follower. This is only valid for roller or curved followers. And then we also have the pitch curve, the locus of the center line of the follower. So each of those items we handled, except for eccentricity, didn't appear on that page. Now we also have pressure angle phi. Again, for a roller follower, is the complement of the transmission angle. And so here we have the transmission angle, and here we have phi, and together they make a 90-degree angle. So the question would be then, how do you go about determining, first of all, this original angle, this transmission angle? The way that you do that is that at a particular location, in this case the follower is moving up and down here, and the cam has been rotated into this particular orientation. So we draw a line tangent through the follower's tangent to the prime circle radius here, and I'm sorry, that is actually the pitch curve. I made a mistake here. Yes, so we're drawing it tangent right here to our pitch curve, and it's a slightly different orientation, but you see here we have a common tangent that goes right through the center of our follower. It's tangent to the pitch curve at that particular location, and then we have another line coming down through where as the follower moves, and that angle is the transmission angle. And to create 90 degrees, we then add the angle phi to it, which is our pressure angle. The force goes from the cam to the follower along the axis of transmission. This is our axis of transmission. It is perpendicular to the axis of slip, which was that tangent line. It's perpendicular to the axis of slip, tangent to the contact surface. As we work on this design, one thing we'll be looking at is that pressure angle phi. Again, that pressure angle phi is to complement to the transmission angle. The two together make 90 degrees. We're going to be trying to keep that pressure angle less than about 30 degrees. That's one of our design criteria. Now, to relate cam rotation to follower motion, so in other words, as this cam rotates, this follower moves, we use instant center of zero velocity to do that. So consider the instant center to relate the cam rotation to the follower motion. I'm going to go through a couple of steps to show that. In this first figure here, what I want to focus on is the fact that we are used to dealing with instant centers, not so much with cams, but we have dealt with them a lot with the traditional all-revolute 4-bar. And so what I've done here is shown an image where a all-revolute 4-bar is kind of superimposed on top of the cam follower. And so you see a ground link here, a crank, a coupler, and a rocker. And you do that, the place where a line through the ground, or parallel to ground, here right through these two joints, and another line that lies right on top parallel to the coupler, where those two lines intersect is instant center 2-4. That instant center is going to be used to relate the cam rotation to the follower motion. So we see how to find it here. It is found in a similar way if you just get rid of the all-revolute 4-bar that's on top. In this situation, you still have a coupler and you still have a ground, and so it's a little bit more difficult to see when you get rid of it and you deal with a translating follower instead of a rotating follower, like as in this case. And so let's look at it here. Here is our coupler, right? And how is it that I24 ends up in this location? Well, what we need to do is we need to consider where would be this point, right? Because this point was used along with this point to draw the line which intersects with the coupler. Here we have the coupler line, right? The coupler link that goes from the center of our follower to a point on the cam that's the center of the rotation where the follower is currently meeting that cam surface. So this follower is currently right here on that cam surface. The center of that cam surface is here, and so that would be our coupler link. And so we have one line there. Now to find the other line, we need to use this rotation point and the rotation point for the cam. Now this is a translating follower, and so really the rotation point for something moving in pure translation is infinitely far away. And so this point here, which would be 04, is infinitely far along this direction. And so to draw a line through this point and through another point infinitely far away would end up having just another straight line right here parallel to this one. And so this line intersects with our coupler line, and that's our intersection point I24. Okay. So now let's go over to the figure that I've been using on a couple of other pages. So this is a similar figure as on the previous slide, and let's find where that I24 would be. And so here's the center of the cam surface where the follower happens to be touching here, and there's the center of the follower, and so that's our coupler point, that's our coupler line coming down through, and here's the center of our cam, and since this one's moving straight back and forth, the ground location or the rotation point will be infinitely far this way, and so we will draw a line through the center parallel to this line, and so that line and this line intersect both right here, and so that's our instant center I24. And so this instant center location is going to be important to us. What we can say is that the follower's motion is going to be equal to the velocity VI24. And so however this point moves in terms of this cam, and if you wanted to find the velocity of that point right there, you simply need to know the cam's angular velocity, which is generally given to us. So we have some angular velocity for the cam, and this radius at this particular time, that radius does change, but at this particular time that is the radius. So omega cam times this radius is going to actually be the velocity of the follower as it moves up in this particular case, as this cam rotates in this direction. So the follower velocity is equal to a length b. Okay, so let me just go back. I don't think I mentioned that here. This length that we have here, I'm calling the radius, is actually a length that I'm calling b here. Okay, and so let's see how that happens. How are we using b instead of b times omega? And so let's look at that for a second. The vertical follower velocity has to equal the velocity due to the rotation of the cam at I24. And so again, that's omega times b, or this velocity, this v, or s dot. You may recall that we call s the position, so s dot would be the velocity of the follower, is equal to this distance b times the rotation rate of this cam, which is omega. So b is the distance from O2, the ground point or the center point of this cam, to I24. That's our distance b. We can relate the derivative with respect to time to the derivative with respect to cam angle. So s dot is ds dt, right? The derivative of s with respect to time. But that could also be written ds d theta. Remember, oftentimes we did our velocities by taking the derivative of the position with respect to cam angle theta. So to get ds dt instead of ds d theta, we need to multiply ds d theta by d theta dt. Then those two d thetas can cancel. So ds d theta times d theta dt is really omega. So ds d theta times omega, or v times omega. And remember, v can be written as a function of theta, and so s dot equals v omega. But s dot is b omega from here. And so instead of v omega, we have b omega on this left-hand side. So b omega is equal to v omega. Well, our omegas cancel, and what we end up with is that b is equal to v. And so what we have here is that this distance here ends up being equal to the velocity of the follower if that velocity is written with respect to cam angle theta. And so, for example, your v could be inches per radian, and that's of course equal to something, a dimension in inches here. So let's not forget about our pressure angle phi. We need to solve for it to check and make sure that it is indeed less than about 30 degrees. We mentioned that earlier as a design criteria. And so what I have here is two triangles, which I'm going to focus on, a yellow triangle and a blue triangle. For our yellow triangle, we have some eccentricity. Again, remember the line of the follower and the center line here going up from O2. There's a distance here, and we call that the eccentricity, using a little epsilon there. And it goes up to some location D. Remember, that was the radius called, that was the prime circle radius, some amount D that we have there. And so we're going up a little bit less than that actually, because D would be this radius, but we're going up this far, and we're calling that variable D. So epsilon and D. Then we have this bigger kind of turquoise looking triangle, and from here to here, so the whole is B, but it's minus epsilon, so it's B minus epsilon. And then we go up to this point. The angle here is that pressure angle. You may recall that pressure angle is written up in here in this range, and again from A down to the instant center I24, which we're calling B. So what is this total distance here? This total distance is going to be equal to S plus D. The smallest it could get would be D if the cam was rotated back around, but it may be a little bit of extra distance. So here's our position, and this is as far down as that follower could ever go, which we're calling a variable D. So what is that D? That D could be represented as RP, RP squared minus E squared, right? Because we're talking about a distance here that is D, where this is the radius, our prime circle radius. And so if we need this side, then we have the hypotenuse, and we have the part, the epsilon part here. So the RP squared minus the epsilon squared square root will give us this D term. And for our angle here, we're going to use the tangent. So the tangent of our pressure angle phi is equal to our opposite over our adjacent. Our opposite is B minus epsilon, and our adjacent is our S plus D. And so we already have the D as RP squared minus E squared square root, so we put that in here. And in the numerator, this B, remember from the previous slide, was equal to V, so we have V minus epsilon. So here's our pressure angle. The tangent of our pressure angle is equal to our velocity, again something like inches per radian, minus epsilon divided by s, which is a position, plus another distance. Okay, and so our units are okay. We have something like inches divided by inches, and so that's great for our units. And so we could, using this equation, determine, taking the arctangent of this equation, we could determine, of this fraction, we could determine the pressure angle for all time, because we have a velocity as it changes. We've been doing plots of velocity, and we also have plots of our position, and we just need to subtract off our eccentricity here, which is just going to be a value that doesn't change, and the size of our cam, this RP, or the prime circle radius, relates to the size of our cam. So S and V come from our profile generated earlier. Our task is to choose RP and epsilon so that we maintain a value of V less than about 30 degrees. To do this, we generally start with an epsilon of 0. Okay, so when we go to determine how big our RP should be, we generally are going to start with an epsilon of 0, and then we're going to adjust RP. As we make RP bigger, of course, our entire profile, our entire cam is getting larger. Okay, because if you notice, as RP increases, this entire structure for that cam is going to get bigger. So we don't want some huge RP. So the way to proceed to determine what the RP should be, if we're not given a RP that we must use, is that we start with the eccentricity of 0, then we adjust RP up and down, and we watch as phi varies. And at some point, we should have an RP big enough to have a phi that's less than 30 for the entire profile, the entire 360 degrees of cam rotation. Generally, the larger our RP, the smaller our phi will be, or the smaller our pressure angle will be. We must also maintain a minimum radius of curvature for the pitch curve. You see here that we have kind of an interesting situation. We have a quite large follower, and then we have a cam shaped here, kind of in pink. And if you notice, there's a little portion here where we have a minimum radius of curvature for this cam, and it comes in here pretty sharp, such that the follower will never actually touch this portion. And so what has happened here is that this particular cam, and remember, this cam is going to, the coordinates of this cam are based on our position, velocity, acceleration, and jerk profiles. It has produced a surface that cannot be realized by the size of this follower. And so what we need to always remember to do, we have another requirement here, not just that the pressure angle be less than 30, but also that the minimum radius of curvature be 2 to 3 times the size of our follower radius. Okay, and so we don't want to have a situation like this. We want to make sure that this guy gets a lot bigger than it is currently. It needs to be 2 or 3 times the roller follower radius. Okay. How do we determine what the pitch curve is for a particular cam? Well, here's the equation for you. You do not have to memorize this equation, but this equation, of course, again, just like the pressure angle, changes for every position along our cam from 0 to 360 of that cam rotation. As we go around this particular cam, we'll have different values of the pitch curve, or the radius of curvature. And the values that you see here are the RP from the previous slide, right? This is our prime circle, excuse me, let me make sure I'm giving you guys the right thing. Right, the prime circle radius is a part of that equation. We also have our position, we also have our velocity, and in the denominator we even have our acceleration. And so remember, all of these various items, the S, the V, and the A, have to be with respect to radians. Well, the S is not, it's just a straight inches, but our V would be inches per radian, and our acceleration would be inches per radian squared. Now it's time for us to machine the cam surface, and to do that we need to find out what is the XY coordinates that our machine tool will follow, and these are those equations. To machine the cam, the machine cutter follows the pitch curve. So the equations for the coordinates of the follower or the cutter tool moving around a stationary cam are given as follows. We have a lambda, which is 2 pi minus theta. Again, our theta goes from 0 to 360, minus the arctangent of our eccentricity divided by our s plus our d. So then the x coordinates of our cam are as follows, and the y coordinates of our cam are as follows. And so there's a lot there. This is really a matter of first determining the table, doing our normal cam design, getting values for S, V, A, and J, and then making sure that we pick a prime circle radius, which results in a pressure angle that is always 30 or less, and also choosing a follower radius such that it is always that the, let me make sure that I'm saying this right, such that the minimum radius of curvature of our pitch curve is always at least 2 or 3 times as large as that rotor follower radius. Once we've done that, we're ready to plot the x and y, or generate these x and y's and send them off to our CNC machine to cut out our cam surface. And that's all I have. Thank you for watching.